evening everyone. Last time we have learned about beats. Okay, the beat is a phenomenon that occurs when there are two sound waves with different frequencies superposing with each other. Right? Again, an essential feature of beats is that we hear beats at a frequency called FB or F beat frequency, which is equal to the modulus of F1 minus F2, right? The difference of these. And I told you that it's not possible to hear too many beats in 1 second, right? If you remember what we heard last time, up to 10 still okay, you can hear it, maybe 10, 12, 13, 14 possible. But once you go 15 and onwards, it becomes very difficult to hear beats. So you could say that for beats to be heard properly, the difference of F1 and F2 should be small. Is this fine? Again, that's an essential condition for humans to hear beats. Clear? Is this fine? Okay. Right. I'm surprised very few of you understood that. Never mind. Let's go on to the next topic now. Let's go on to the next topic, and that is Doppler effect. Okay. So, what is Doppler effect? Doppler is actually the name of a person, right? Okay, but this effect has been known for I think about 2 centuries now, right? So, very well understood phenomena. See, a very good example of Doppler effect happens at the railway station, right? Have you sometimes, if you have been to the railway station, you might have noticed that if you are standing here and if a train that is not supposed to stop at the station passes by fast, have you noted that as it passes you, the sound of its whistle changes? Have you noted that? This also happens with cars as well. Not necessarily train only. Doppler effect has nothing to do with train as such. Let's say you are standing on a highway, right, next to it, and if a vehicle which is blowing its horn passes by fast, then also you are going to see that as this moves, the sound seems to change. Now, I am not talking about loudness. See, I am not talking about loudness. Right? Of course, obviously, when something will come close to you, loudness will increase. Right? No, that's not what we are talking about. Right? Loudness is something related with amplitude. Let's be very clear about it. I mentioned it the last time as well. Loudness of sound, how loud is the sound, is related with the amplitude. Clear? Right? But I am talking about pitch. Right? I am talking about pitch of the sound. Okay, pitch of the sound is related with the frequency. Right? Pitch of the sound is related with the frequency of the sound. Right? What is pitch? Pitch indicates the type of sound. For example, if you compare two different sounds, let's say a buffalo's sound, and you compare that with a whistle, right? Compare the sound of a buffalo and that made by a whistle, right? You see the difference between these two is the pitch. Whistle sound is high pitch. Okay? The sound that is harsh on our ears, right? Okay? A very sharp sound. On the other hand, buffalo's sound is low pitch. Did you understand? You can replace buffalo with any animal of your choice. Okay? A lion, a cow, alright? Yeah, but not a dog. Understood what is meaning of pitch? Right? So basically, high pitch means high frequency. High pitch means high frequency, and similarly, low pitch means low frequency. Right? Okay? So pitch is something that is related with the frequency of sound. Right? Okay, generally female voice has low pitch and female voice has high pitch and high frequency. Right? On the other hand, male voice has low pitch and low frequency. Okay. Nevertheless, let's continue. Alright, so I am not talking about loudness when we talk about Doppler effect. It's that as this comes close, obviously loudness will increase. No, we are not worried about that. We are worried about this. As this comes close, we see a change in the frequency, and we can notice a change in the frequency of the sound. Right? That's what Doppler effect is. Let me just write it very quickly. What is the Doppler effect? Due to relative motion, relative motion is bad. Due to relative motion between source and observer or listener. In case of sound, you can also use the word listener. Okay, someone who is listening to the sound. So due to relative motion between source and listener, the apparent frequency, or rather you could say frequency heard, right? The one that you get. Frequency heard by observer is not same as frequency of sound emitted by source. Okay, due to relative motion between the observer and the source. Okay, what happens is that the frequency that is heard by the observer is not same as the frequency that is emitted by source. Let's take an example. Suppose source is emitting a frequency 400 Hz. Right? Suppose source is emitting a frequency 400 Hz. Let's say source is here, and here is observer. S for source, O for observer. Okay, let me just clarify that. Next time I will not. Suppose this source is moving. Let's say this is a moving vehicle. Did you understand? Let's say this is a moving vehicle which blows horn, and observer is standing over here. Then there is relative motion between them. Now because of this, what will happen is that when this sound which was emitted from the source, when it will reach the observer, the observer will not hear that as 400 Hz. In fact, in this particular case, when the source is moving that side, it will be greater than 400. Okay, the frequency that is heard by the observer will be greater than 400 Hz. This is what happens. I have not yet told you why it happens. Alright? I have not yet told you why it happens. Right? I have only stated what happens. Okay? So now, let's go to why it happens. Okay? Let's go to why this kind of phenomena occurs, where the source emits a frequency 400 Hz, but still the observer listens to a different frequency, right? Okay, so let's talk about that. Again, it's all here. All the secret lies in this. Okay, relative motion. Well, so you can actually understand this effect. Listen to this. You can actually understand this effect in two different cases. One case where, let's say that source is moving and observer is stationary. Okay, so first we will talk about this, where source is moving and observer is stationary. Also, let me just give you a note. we will talk about, generally I explain things using 1D motion. Okay, do you remember one dimensional motion, motion in straight line? Okay, alright, I will explain this using one dimensional motion. Okay, what about two dimensional motion? Does Doppler effect not occur in two dimensional motion? It occurs, right? But just like we learned it in earlier chapters of 11th standard that in case of 2D motion, all you have to do is take some components and treat it independently in both directions. Okay, so there's not much difference in the concept. So with 1D motion, it's very simple to understand. Let's start. Okay. So for explaining this straight away in the simplest manner possible, I'm going to take over the screen, right? Okay, just give me one moment. Kind of things, it's very easy to explain by using animate. Oh, here we are. Okay. Right. Can you see the screen, everyone? Wait. So over here, what we are seeing is we have some controls, okay, about velocity of source and observer. So first of all, we are going to consider a case where source is moving, let's say with some velocity. Okay. Right. We could actually set it to anything, right? Values are not that important when you just want to understand concept. Okay. Now here, what is given is that this source is going to move towards the observer. Right, this source is going to move towards the observer, typically with a speed less than speed of sound. See, speed of sound in air is about 340 meters per second. You can see my cursor, am I right? Can you see my cursor? Okay, very good. Yeah. So 340 meters per second is the speed of sound in air, normally, right? Or about 340. But we are considering the source speed 200 meters per second. Okay, that means this blue source is going to move towards the observer, right side positive. Okay, that's why this is positive. Towards the observer. Observer will remain stationary. So when I play this, we are going to see green colored circles. Right? We are going to see green colored circles. So what are those circles? They are indicating the crests, okay, of the sound wave. What do I mean? Okay, first of all, to explain what I mean here, let's make this velocity 0. I hope you can make it 0. Come on. Okay, yeah, done. So now you see what happens. Alright. Okay, what are these circles? See, after every time period, it's going to emit one crest, right? When the wave is emitted, it will emit crests. Is that clear? Is it clear what this is? No, probably not. Okay, for a moment, let's go to the board, everyone. For a moment, let's go to the board. So suppose here is sound source. Okay, this is the source. S for source. At start, it will emit one wave. Now that wave will go in all directions. Think about it. If you use a speaker and you put it at one point, the sound from the speaker goes only in one direction? No, it spreads out in all directions. So what will happen? When this will emit, after one time period, the wave would have traveled some distance and now the crest would be here. Again, one more time period will pass, this will move forward and we will have one more crest. So basically this is equivalent of here is source and it starts emitting. So as it emits, the wave travels forward and forward and forward. Is that clear? But here it is going in every direction. So equivalent diagram would be something like this. Okay, like this, the sound wave is traveling forward. And these circles, they are indicating locations of crests. Did you get it? After one more time period, one more circle is formed. After one more time period, one more circle is formed. Clear or not clear? Okay, so right now we are seeing that the source is stationary. So what is the distance? Listen to this carefully. What is the distance between two consecutive circles? Is going to be wavelength. Is that clear? The distance between two consecutive circles is wavelength. Is that clear? Because I said every circle represents crest. Every circle represents the position of crest. So gradually as time will pass, you see the wave is traveling forward in all directions. In which directions? In which directions? Let's see. Okay, suppose I put it that way. The wave is traveling in this direction, in this direction, in this direction, in this direction, here, here. Did you understand everything? Alright? So distance between two consecutive crests is of course lambda. So all these are indicating crests. Okay? Fine. Let's proceed forward. So this is what happens. This is what happens when the source is not moving. Right? Very good. Source is not moving. Well done. Right? Nothing extraordinary. Why? Because even here for the observer, the distance between the two the crest will be lambda. Do you realize when the wave will reach observer, the observer will see, okay, distance between two crests is lambda. Very good. Nothing extraordinary. Fine. Okay. Let's see what happens next. Let's reset this. Let's say the source is moving with some velocity. Don't look at the numbers, okay? Numbers are not important for us, the concept is important. Then I tell you how to calculate these numbers. It's a very easy thing. Okay, so let's say the source velocity is 100 meters per second, very fast. Alright, towards the right side, let's start. Okay, do you see something strange happening? What is going on? Because the source is moving, distance between two crests on one side has decreased. Do you realize this? This distance is less than this distance. Yes or no? No, it is not decreasing, but it has decreased. On the right side, all these distances are same. You can check that. If you want, you can take a ruler, put it on your screen, and you can check. All these distances are same. They are not decreasing, but just that on the right side it is less, and on left side it is more. Did you understand? Did you understand or not? Yeah. This is where Doppler effect has occurred. Right? So why is it like this? Why is it like this? Come to the board, everyone. Come to the board. Suppose source was here at some time and source emitted wave. Let's say. Okay? So the wave emitted by the source or the crest emitted by the source has reached as a circle, it has reached here. I am trying to draw a perfect circle as much as possible, okay? So please excuse me. Yeah. Let's say the circle or the crest has reached here. But we know that after emitting the crest, let's say the crest traveled like this, bigger and bigger and bigger circle. Okay, crest traveled like this, bigger and bigger circles. But by the time the crest reaches from source to here, the source itself moves. Let's say the source moved right side and now the source is here. Now do you realize that when it will emit the next circle, what will happen? On this side, the distance between circles is more, but on this side, the distance between circles is less. Did you understand? Did you understand? So what does this mean? What does this mean? On one side wavelength is different and on the other side the wavelength is different. Is that clear? These wavelengths are not same. Yes or no? Okay. Very. Now where is observer? Observer is on this side. So what is the observer receiving? Is the observer receiving the same wavelength as in stationary case? Or is the observer going to receive less wavelength? What do you think? Is the observer going to receive same wavelength as in stationary case? Or is the observer here going to receive less than that? Less wavelength or more wavelength? Less wavelength. Very good. Less wavelength. Right? I hope you realize why it's happening. Because the source starts to move on that side. So the two waves will come close to each other. Did you understand? The two waves will come close to each other. Now, what does that mean for frequency? Let's talk about that. Let's talk about that. You see, I told you earlier that wave speed depends on come on, complete that sentence. Wave speed depends on very good, Ankita. Others, it would do well if you would remember the basics. Without that, building upon the chapter is a little difficult. Vishwa to out, well state out to jo. આવા આન્સર આપે રોહન તારો એ વારો છે આવો wave speed depends on medium or on properties of medium and has nothing to do with source. Correct or not? And has nothing to do with source. Clear? Clear or not clear? આવું લખાયું હતું ને વાંચો જરા વાંચો Okay, so what does that mean? Why am I bringing that up here? What this means is source can remain stationary, source can move here if it wants, no problem. Wave speed does not depend on source. Clear? Clear or not clear? Even if the source moves, wave speed does not change. Understood or not? Wave speed does not change. Clear? Okay. So now V equal to F lambda is what we are going to use. So if you will compare two cases, here when the source was stationary and observer was also stationary, case 1, okay, no motion going on. So here V is equal to F1 lambda 1. What is F1? The frequency heard by this person or this observer, okay? F1 is not source frequency, okay? It may be different. I repeat, when both are stationary, F1 and Fs are equal. I mean frequency of source. Fine. But when the source is moving and the circles formed are not like in the first case. They are like this. Okay? So then this lambda 2 and this F2, we are going to talk about that. Do you realize that this lambda 2 is less than lambda 1? Like here, if the observer is here. Do you realize that lambda 2 is less than lambda 1 for the observer on that side? Yes or no? Is this clear? Okay? Right. So if lambda 2 is less than lambda 1 but V is same, remember, V is same because it doesn't depend on what source is doing. That's why F2, which is equal to V by lambda 2, right? Okay, and here F1 was V by lambda 1, right? So clearly, because lambda 2 is less than lambda 1, F2 will be greater than F1, but F1 is same as frequency of source. So F2 will be greater than frequency of source. What does that mean? Doppler effect. What this means is, suppose the source is moving towards the observer. Suppose the source is moving towards the observer. Then, when the observer listens to that sound, the frequency of that frequency of the heard sound, the listen thing, will be greater than the frequency of source. So again, exactly like the example I gave you at start. Even if source frequency would be 400 Hz, for example, then it's possible that this observer, when the observer will listen to that frequency, right? When the observer will listen to that frequency, it will be greater than 400 Hz. Is this clear based on this situation? Okay, read the meaning of Doppler effect. What's the meaning of Doppler effect? That due to relative motions, the frequency heard by the observer is different from the frequency of source. Clear? Frequency of source would be 400, for example, but frequency heard by the observer is greater. Okay, fine. What about observer on the other side? What about observer on the other side? Okay, let's talk about what if the observer was such that source is not going towards the observer. Okay, source is not going towards the observer, but source is going away from observer. Right? So let's clear this everything out, okay, and see it again. So this time, let's say source moves towards the left side, negative velocity, everyone, left side. Alright? Okay? So source will try to go away from the observer. Let's see what happens. Do you see when these waves will reach the observer, the wavelength would be more this time? Do you realize that when the waves would reach the observer, the wavelength would be more? This wavelength would be more compared to on the other side. Okay, let's just take a little bit back. All right. Okay. Yeah. Have a look here. So we are seeing that this distance is clearly more than the other distance. Right? Okay, so what is happening on this part is reverse. Right? But the Doppler effect is going to happen in a reverse manner. What does that mean? Here, okay, come to the board now. Come to the board. So if the observer is not on the right side, let's say here we are considering the source is moving towards the left. Okay, I'm drawing it here. This would be a good. So source here, and gradually the source is moving towards the left side and observer is towards the right side. Then if the source comes here and then emits the next circle, it would be like this. Correct? So now the wavelength over here on this side is more. Understood? More than what? More than this lambda 1. Suppose I call this lambda 3, then this lambda 3 will be greater than this original wavelength. Is that clear? This lambda 3 will be greater than this original wavelength. So if lambda 3 is greater than original wavelength, we will have F3 less than original frequency. Is this understood or not? By proportionality. Okay? Same kind of calculation that we did earlier. Right. So everything clear about source moving? So when source moves, what is changing? Wavelength is changing. Everyone understood that? You can write it. You can write it. I'm speaking it again. When source moves, wavelength appears to be changed. When source moves, wavelength appears to be changed. So frequency changes. When source moves, wavelength appears to be changed. So frequency changes. Alright? That means Doppler effect has happened. Alright, now let's go to the other case, everyone. Where suppose case 2 now. Case 2. Source is stationary. Okay, and observer is moving. Source is stationary and observer is moving. Again, observer means listener, don't forget that. So this time, do you realize that the circles are just going to be simple ones because the source is not moving? Yes or no? Is this clear? What I've drawn? Why source point is changing its point? Gracie, what is meaning of source is moving? What is meaning of source is moving in the first case? Come on. Source is moving, that's why it's changing its point. Okay? So now here the source is stationary. Source won't move. So just more crest coming like this as concentric circles. Alright. So suppose observer was also not moving, let's say, for example. Then observer just sits over there. Then one wave will come, the second will come, the third will come, the fourth will come. Like that, the wavelength will be lambda. Very good. Fine. But listen to this carefully. The velocity, listen to this carefully. Wavelength is lambda, no problem with that. But velocity of sound with respect to observer, be careful with this. Velocity of sound with respect to observer. When observer moves, do you realize that velocity of sound, okay, with respect to observer, V sound O, I am writing like that, okay, at the moment. Do you realize that this should be velocity of sound minus velocity of observer? Understood or not? Understood or not? Relative velocity, we have learned it very early in 11th standard. Alright, we are using that concept. Nothing extraordinary here. Nothing. When observer is not moving, everything is normal. Suppose observer is not moving, V0 is 0. Fine, everything okay. And we could just do V equal to F lambda or lambda. Fine. But what if observer starts to move? What if observer starts to move, let's say, away from this source? Then do you realize that for observer, if an observer is going away, let's say observer is going in this direction, then do you realize that for observer, relative velocity of sound is less? Yes or no? Do you understand this sentence? If observer starts to go away, the relative velocity of sound for observer becomes less. Clear? No समझा तो the doubt पूछ दो. Only 4 people are raising hand. I cannot know what's in your mind, right? Okay. Alright. So now, if V will decrease, listen to this carefully. See, this is the strange thing. Wave speed we know does not depend on source, fine. But if observer will move, relative velocity will change. Do you understand what I am saying? If observer will move, the relative velocity of sound with observer will change. That's where the magic happens. So if V will change, then one of these two have to change, correct? You understand what I am saying? If V will change, velocity of sound with respect to observer, okay, if that will change, one of these two have to change. Understood or not? What should I repeat? What should I repeat? If there are two vehicles going in same direction, their relative velocity is less. I hope you realize that. Okay? Two things going in same direction. Sound travels from source to observer. Right side. Observer also going towards right side. Suppose sound velocity is 340 meter per second. Observer velocity is 5 meter per second. Then their relative velocity is only 335, not 340. Did you understand? It's less. Clear? Okay, so I was saying, I was saying that one of these two has to change. If V is changing, one of these two has to change. Now, what about wavelength? Let's talk about wavelength. Do you realize that again, wavelength is just the distance between these circles, right? Observer moves, that cannot change these circles. You understand what I am saying? Circles depend on source, yes or no? So whether observer moves or not, these distances are always lambda, yes or no? Okay? So what does that mean for us? What does that mean for us? That lambda is not going to change. Observer can come close, observer can go away, no problem. Lambda will not change. Understood? You can just put it here. But lambda, that is wavelength, will not depend on motion of observer. Did you understand this sentence? Okay, lambda will not depend on motion of observer. Right? We are going to see that very soon on the animation also. Alright, just give me one more. Let me finish the maths here and then we'll go to the screen. Okay? So, if lambda is not changing, then f has to change, right? There is no other possibility. If lambda is not changing, f has to change. So here as v has become less, okay, as v has decreased compared to speed of sound. So that is, I can say that v of sound with respect to observer is less than speed of sound in air. Is this clear? Because of this, frequency heard by observer, okay, is going to be less than frequency of source. Clear or not clear? Based on this relation. Clear or not clear? But remember, why is this relative velocity less? Because observer is going away. We were talking about a case where observer is going away. Now consider a case when there is source, okay, and observer is moving towards the source. Then what will happen? Sound going that way, right? Sound will go from source to observer. Use common sense. Don't fall into confusions. Sound always goes from source to observer, correct? When you listen to sound, sound is going from the speaker. Let's say you are listening to music. Then sound is going from speaker to your ears, correct? So sound going that way, so velocity of sound is on the right side, okay, and velocity of observer is suppose left side. Then their relative velocity is more. I hope that makes sense. Okay, so that's why V sound with respect to observer, if it will be greater than velocity of sound in air, what will happen? If the relative velocity is more than velocity, then that would mean frequency heard is greater than frequency of source. Understood? Understood or not understood? Guys, I am not seeing your hands. Alright, fine. Now I have come to the computer here on the screen now, everyone. Let's see. Okay, so let's play this, but this time we will make the observer move and suppose source is stationary. Okay, and so first of all, let's play it just like that. So you see the circles are there. You're going to see that the circles are still the same way if observer is moving. Let's say observer is going away towards the right side. You see, circles are still the same. Do you realize what I am saying? Do you realize what I am saying? Circles still the same because source is not moving, right? Because the source is not moving. Now what will happen for the observer? Okay, this is where you can use the idea. You can take advantage of animation. Suppose source observer velocity is really more. Let's say 80 meters per second or suppose 100 meters more than that. So you see what will happen. Okay, I hope sound will reach the observer at some point. Sorry. Unfortunately, we cannot move the source. The observer or the source. Otherwise, they will definitely right. See, we are running into a problem. Fine. Okay. This is just the moment where the first crest has been observed. Now, imagine for a moment that observer is stationary. Right? Imagine for one moment that observer is stationary. Then this wave will come here and it will reach the observer. Correct? Okay, in some time. But now, what will happen is that because the observer is running away, we realize that the wave will take more time to catch the observer because the observer is also running away. That's what I am saying. The observer runs away from the wave, right? That's why the relative velocity is less, and because of that, the observer will receive less number of waves. That's why the observer will receive less number of waves. What is meaning of number of waves? Frequency, isn't it? Frequency means number of waves received. Yes or no? Okay, let me give you one powerful analogy. Okay, listen to this. Suppose you are standing here. Alright? Suppose you are standing over here. And someone is throwing balls at you continuously, one after the other. So if you stand over there, how many balls will hit you in 1 second? Some balls are thrown. So they all move towards you with some velocity and they hit you. Alright. But do you realize that if you start moving backwards slowly and slowly, right? If you start moving backwards slowly and slowly, then that would mean the gap between the gap or duration or interval between hitting two balls would increase. Yes or no? If you start to go backward, yes or no? That's it. This is Doppler effect. What happened here? What happened here? It was earlier like when you are stationary. When you are stationary, you would receive, let's say, 3 balls in 1 second. So the frequency would be 3 Hz. Right? That the frequency would be 3 Hz. But instead of that, if you start walking backwards, then less number of balls will hit you. Did you understand? बस तो आउट છે. Okay. Perfect example શું વાત કરે છો? It's not perfect in every way. There are people like me can find problems with this example also. Don't worry, okay, I have read your question. Just give me a moment. Okay. So there is a good question here. What if observer runs away very fast? Okay. Yeah, this is perfectly possible. In fact, I'd rather show it in animation. Immediately it would be clear. The question is, what if the observer moves so fast that wave never reaches it? Okay, if sound never reaches it, yes, possible. Right? You can do that. If this allows. Yeah, fine. Let's say this is 343 meters per second. Alright? Maximum 343 is allowed. And here this source will emit waves. So those waves will never reach observer. Why? Because the observer is also running away. Okay? Have a look. You get what I am saying? It's like someone is chasing you at speed 50 meters per second. And you also run away at speed 50 meters per second. That person can never catch you. Understood? You are, right? Opposite is also possible. Right? That's actually called sonic boom. Right? Opposite is also possible. Wow,